Good morning all. Today we are going to learn about two types of interprocess communication techniques such as RPC and shared memory. This RPC or remote procedure call is used for communicating between two processes working in a different system. Here one process will send a subroutine to another process, and that process will execute that subroutine and return back or send back the result to the original process. So it is a little bit different from all other types of interprocess communication, because in almost all the interprocess communication we are sending the data from one process to another process. But here in RPC method we are sending a subroutine to one process to another process. And the next one is the shared memory. Here in the shared memory we are using a shared memory segment for communicating between two processes, and it is a lot faster than all other types of interprocess communication, because for shared memory interprocess communication we don't need to use the operating system services for communication. These are the outline of this session. Initially we will discuss about RPC or remote procedure call. In RPC interprocess communication we will send a subroutine to the remote server for further processing, and after processing the subroutine in the remote server will send back the result to the client machine. And we will see various techniques used in the RPC implementation. Then we will move on to the shared memory concept. And after discussing about shared memory we will see the mailbox. It also is an interprocess communication, and it is more like it is similar to message queue. Now we are going to learn about RPC or remote procedure call. This RPC or remote procedure call is an interprocess communication method. Since it is an interprocess communication method, we can communicate between two processes using this RPC. And this RPC is little different from other types of interprocess communication method such as pipe, socket, signals, etc. Because in RPC we are executing a subroutine in different systems, but in the case of signals and pipe and socket we are sharing data between two processes. And so this RPC method can be thought as it is a method of executing subroutine in different address space. It means that it is a method for executing subroutine in different computer in a shared network. Did you ever use FaceApp, an Android application for changing the gender of the image? You probably did use a FaceApp. And here in the case of FaceApp they are using an remote procedure call for processing the image. And in the image processing section the FaceApp uses a remote procedure call, and this remote procedure call will send the image, captured image or image from the gallery. They will send it to the FaceApp server, and the FaceApp server will make the necessary tweaks on the image and send back to the Android application. Here the application will download the image and show it on the display, and they will also provide some functionality to save the image. So here in the image processing part of the FaceApp is done entirely using a remote procedure call. Along with the FaceApp Android application, this RPC method can be used in many other application scenarios, such as it can be used in online Word editors, online PDF converters, online image processing softwares, and much more. And recent evolution of the smartphone technology also improve the significance of this RPC methods, because the smartphone has a limited resources. It means that it has limited performance and it has limited memory capacity. So it cannot run a sophisticated task within the time bound. So we will use a RPC method to run the sophisticated task in a highly performance cloud computing environment, and the cloud computing environment gives the result back within the time limit, so we can improve the overall performance of the application. The RPC calls is similar to regular function call, so the programmer can easily code the application. But this RPC calls and regular function calls are not identical. It can be easily distinguished from a regular function call. So it is saying that the RPC model implies a level of location transparency, namely that calling procedures are largely the same whether they are local or remote, but usually they are not identical. So local call can be easily distinguished from remote calls. RPC is implemented via a request response message passing system. It means that there will be one client application and there will be one server application which is higher performance than client application. And when a RPC method is invoked in the client application, it will send the RPC request to the server application. Along with the RPC request, it also sends the required parameter to the server application. The server application will perform the operation on this parameter and send back the result to the client application. Since this RPC method involves a data transfer between client and server, it will be a order of magnitude slower and less reliable than local calls. So the programmer should consider this fact during the design of the application. This is the timing diagram of message passing in an RPC method. Here we can see there are one client and there will be one server. Client is a low performance device. It can be a computer or a mobile device. Server is a high performance device which has higher performance speed and higher memory capabilities. So in RPC method, the client, when executed a RPC subroutine, it will send the RPC request to the server, and along with this request, RPC request, client also send the required parameter. So the server will process the request in a bounded time and it will make a response from the output data and it will send it back to the client application. Upon receiving this response from the server, the client application will continue execution. During the time of this RPC, the client will wait for the result. So this time client will be in blocking mode. In the previous slide, we have studied about the timing diagram of the RPC implementation. Now we are moving on to the RPC implementation setup or the block diagram of RPC implementation setup. Here you can see there are two devices, client device and server device. Here the client is a low performance device, but the server should be a high performance device because it has to handle multiple client devices at a time. So the bandwidth and processing power of the server should be higher. In the client device, there will be some application which will call some RPC subroutine. This subroutine needs to be sent to the server. Before sending the RPC subroutine to the server, it has to be pre-processed, or it has to convert the parameter should be converted into a format so that the server can be understood. And this conversion is done by the client step. After the parameter conversion in the client step, the data and subroutine will be sent to the server, and this is done using the client runtime library. This client runtime library is taking care of the data transmission between client and server. And in the server, server runtime library will handle this data traffic. And when the request, RPC request is arrived at the server step, it will convert the RPC request and RPC parameter to the application readable format. Then the server application will execute this RPC subroutine and send back the result to the client. Now we can look deep into client step and server step. A step is a piece of code that converts parameter passed between client and server during a remote procedure call. It means that for a remote procedure call, we have to send some parameters, and the conversion of this parameter or processing of the parameter is done by the client step and server step. We can understand this feature by an example. Suppose our client application is made by C or C++ language, and in a remote procedure call invocation, our client application sending some parameter to the server, and server perform the task based on the remote procedure call and the parameter. If the parameter contains some pointer values and client sending these pointer values directly to server, then the server cannot understand the data at the pointer location, because both client and server are operating at a different address space. So when the server is trying to access the pointer location, it will get a wrong data or it will get an error. So such times the step will help to process the data or convert this pointer data into a real data, and this is achieved using this client step and server step. Here the client step and server step are doing the necessary data conversion procedure for remote procedure call. So the applications in the server and client need not to worry about the data conversion procedure. So they can treat this remote procedure call more like a local function call. So it says that the step perform the conversion of the parameters, so remote procedure call look like a local function call for the remote computer. And another advantage of this remote procedure call step is that the client and server may be using different data representations. Suppose client is using little endian mode and server is using big endian mode, and if the conversion between this data representation is not happen, then the remote procedure call cannot be completed successfully. So this conversion between this data representation is achieved using this client step and server step. Now we can go through the functions of client step and server step. This client step and server step has mainly two functions. The first one is marshalling and the second one is unmarshalling. Marshalling is the process of transforming the memory representation of an object to a data format suitable for storage or transmission. For example, the pointer data type is not suitable for storage, because when the application get restarted, the value of the pointer location will be changed. So in the marshalling function, the step will taking care of this type of data types, and it will store or transmit in a more suitable data format. And during the unmarshalling, this stored data type is converted into the original data type, and here the step doing the inverse of the marshalling, and so it is called unmarshalling or demarshalling. The next functional block of the RPC system is the RPC runtime. This RPC runtime system is a library of routines and set of services that handle the network communication. Because this client application and the server applications are running in different systems. So for the proper operation of this RPC calls, there should be a consistent and reliable communication between these two systems, or this client system and server systems. And for this communication between this client system and server system, we can use the RPC runtime libraries. And using these libraries, we can achieve a reliable communication between the client application and the server application. And along with these libraries, this RPC runtime also has some services, and which also help to manage this communication between client device and the server device. And RPC runtime functions are core handle binding, establish communication over an appropriate protocol, pass call data between client and server, and handle communication error between client and server. Now we can again visit the RPC implementation steps in detail. Here you can see there are two machines, client machine and a server machine. The client machine containing one client application and the server machine containing one server application. When the client machine invoke a call and invoke an RPC call, it will give the RPC call along with the parameter to the client step. Client step will do the necessary packing of the parameter, received parameter, and given to the RPC runtime. And this RPC runtime will send the data through a communication channel, and this will be received by the RPC runtime in the server machine. And this RPC runtime again give this data to the server step for unpacking. After unpacking, it will given this data to the server application. So server application will execute the RPC method, and it will return the data to the server step. So server step will do the necessary packing of the data for data transmission, and it will given to the RPC runtime in the server. And this RPC runtime in the server will send back the data to the RPC runtime in the client, and this RPC runtime given the data back to the client step. So the client step do the necessary unpacking of the data, and it will given to the client application. So the client application will continue the application next application instructions. Now we can see various examples of RPC. The first three examples of the RPC are language specific RPC. Here the RPC for the Java is called Java RMI or Java Remote Method Invocation. And RPC is an RPC mechanism which is used solely in Python language. And distributed Ruby is an RPC mechanism which is used in Ruby language. And below these are the general purpose RPC methods. And example of these general RPC methods are Apache Thrift, dbus, SOAP, XML RPC, JSON RPC and embedded RPC. We are moving on to shared memory. Shared memory is a type of interprocess communication method. And using this shared memory, we can achieve the communication between multiple processes. And shared memory is nothing but a block of memory which is shared between multiple processes. And using this memory, we can achieve the interprocess communication. Here it says shared memory is a memory that may be simultaneously accessed by multiple programs with an intent to provide communication among them or avoid redundant copies. And in comparison to other types of interprocess communication such as signals, socket, pipe, etc., shared memory is an efficient means of passing data between programs. Because since it uses a shared block of memory for communication, it doesn't need to use the system services for establishing the interprocess communication. So it is more efficient than all other types of interprocess communication. So using shared memory data can be made directly accessible to both the processes without having to use the system services. And for the synchronization of the data access between the processes, the shared memory concept uses a semaphore. And using this semaphore, we can achieve the synchronization for the uses of shared memory access. And it is more faster way for interprocess communication than all other processes because it doesn't need to access the system services for interprocess communication. Now we are moving on to the memory organization of the shared memory interprocess communication technique. Here you can see two processes, process P1 and process P2. Both have some private memories such as stack memories, heap memory, data memory segment, and memory segment for the test section. And these all memories are private to each process P1 and process P2. It means that the process P1 cannot access the private memory segment of the process P2, and process P2 cannot access the private memory segment of the process P1. So in order to obtain a communication between two processes, process P1 and process P2, we are using a shared memory segment. And this shared memory segment is mapped to both the process P1 and process P2. So using this shared memory segment, we can achieve an interprocess communication. Suppose the process P1 need to communicate with the process P2. So process P1 will write some data into the shared memory segment which it want to communicate. And after writing the data into the shared memory segment, the process P2 will read the data in the shared memory segment because this shared memory segment is also mapped to the process P2. So it can directly read the shared memory segment data. So it can achieve an interprocess communication because the data written to the process P1 is able to read by the process P2. So we can achieve an interprocess communication between process P1 and process P2. Now we can see the various stages of shared memory creation. The first stage of the shared memory creation is the process which is requesting the operating system for allocating a shared memory. And upon receiving the request, the operating system will allocate a memory range for shared memory purpose. So the first step of the shared memory creation is the process request to the operating system a memory segment that can be shared between the processes. So upon receiving the request for shared memory creation, the operating system look for a big enough memory address range in the calling process address space and mark the address range as a special range. Changes in the address range are automatically seen by the other process that also have mapped the same shared memory object. So the operating system will allocate a shared memory segment. So each process can see this shared memory segment. So each process can start communicating each other using this shared memory segment. So the process can start writing to and reading from the address space to send to and receive data from other processes. So each process can read and write data into the shared memory segment and attain a communication between two processes. Now we can go through the various functions which is used for the shared memory creation. The first function for the shared memory creation is the ftalk function, and this ftalk function will give a unique key and which can be used for the creation of the shared memory segment. So this ftalk function will create a key to uniquely identify the shared memory segment, and this is the syntax of this ftalk function. Upon executing this ftalk function, we will get a unique key, and this key can be given to the SHM get function or shared memory get function to obtain the shared memory ID. And along with the unique key, the SHM get function also need the size of the memory segment as well as the permission of the memory segment. So this is the format of the or syntax of this SHM get function, and upon executing this SHM get function, we will get memory ID, and this memory ID is given to the SHM AT function or shared memory attach function, and this shared memory attach function will give a pointer location to the shared memory segment, and using this pointer location we can access the shared memory. We can use this SHMDT function for detaching the shared memory segment, and this is the syntax of SHMDT function. Here we will give the shared memory pointer which is obtained by the SHMAT function to detach the shared memory segment. And next function is the SHMCTL function, and this SHMCTL function will remove the shared memory segment when it is no longer needed. And in order to remove this memory segment, we have to give the shared memory ID to the SHMCTL function, and upon executing this SHMCTL function, the shared memory will be removed when it is no longer needed. Today we have studied about two types of interprocess communication techniques, RPC and shared memory. In the RPC or remote procedure call, we are sending a subroutine to the remote server for processing, and after processing, the remote server will send back the result to the client application. Then we have seen shared memory, and it is a fastest way for interprocess communication. Here we are using a shared memory segment for communication between two processes. Since in the case of shared memory, we don't need to use the operating system services for communication, so it is a lot faster than all other types of interprocess communication techniques. Now I am going to wind up this session. Thank you. See you next week.